For years, XOOS module development has been constrained by a single monolithic bottleneck: data handlers tightly coupled to global state dependencies. This structure forces developers to copy and paste the same validation and business logic across every single controller just to get things to work. XMF 2.0 addresses this by introducing a non-breaking architectural overlay. It does not replace the existing foundation, it builds on top of it. This overlay introduces over 141 decoupled components, equipping the CMS with dependency injection containers, event buses, and middleware pipelines. Utilizing this new logic requires a shift in technical requirements. The server must run PHP 8.4 or higher, paired with Smarty 5. Because these components slide directly over existing code, legacy systems can operate uninterrupted right alongside the modern architecture. By isolating operations through API middleware and decoupled routing, developers have a clear path to true test-driven development. Instead of the closed requests of the past, data now flows through standardized, verifiable REST API pipelines. This structural layering allows modern application logic to run alongside the existing core. It creates a footprint for advanced features without requiring immediate modifications to the underlying legacy database. This animated diagram tracks the macro impact of the framework. We see an 87% reduction in the boilerplate code required to build a module, dropping from over 1,800 lines of manual code down to just 245. Looking closely at the specific subdivisions, the drop is starkest in complex features. A media upload pipeline that used to take 150 lines of code now takes 15. An append-only audit trail drops from 200 lines to exactly 10. By eliminating this specific infrastructure boilerplate, developers can shift their resources toward writing pure domain logic. The ideal starting point for new development is the XMF blog baseline structure, which contains the complete blueprint for this architecture. The first step of modernization begins here, by creating the module bootstrap class. This bootstrap class acts as the composition root. As the database, config, and cache services wire together, this becomes the single central location for all service registration. When service instantiation is scattered across multiple files, it creates a brittle, untestable web of dependencies. Now, runtime controllers use constructor injection to pull exactly what they need directly from this centralized container, completely abandoning global variables. Establishing this centralized composition root creates the isolated, testable foundation necessary for all subsequent application logic to function securely. At the data layer, the traditional Zoops object model has always relied on deep, rigid inheritance structures that limit flexibility. XMF uses PHP 8.4 traits to dynamically compose capabilities. Shards slot seamlessly into the entity membrane. Injecting change tracking trait lets the entity track changed nodes. Meanwhile, JSON fields trait safely encodes array matrices into a database text column. These traits are then wrapped by PHP 8.4 property hooks, providing a strictly typed API layer for the developer. Because the hooks call existing base methods internally, this typed layer maintains perfect backward compatibility with legacy data requests. Additional composable behaviors can be snapped in as needed, like the audit trail trait, which manages soft delete lifecycles so no data is ever permanently lost. During a migration, developers add these traits incrementally, testing one behavior at a time. Trait composition enables a modern, typed entity architecture while preserving total compatibility with legacy database schemas. With entities defined, we use the repository pattern to extract all data persistence logic completely out of the controller layer. To handle routing, Table State Manager intercepts and filters data requests for listing pages. The manager strictly controls pagination and enforces explicit sorting allow lists. Malformed query parameters simply ping off the filter, while clean, valid pagination data passes safely through to the database. Pushing data access and request filtering into these dedicated layers guarantees deterministic application behavior, even under highly unpredictable user input. To understand the power user capabilities of XMF, we have to analyze the execution cycle of the module bootstrap. This vertical glowing plane represents the boundary. It strictly separates the configuration phase on the left from runtime execution on the right. The entire object graph, all the dependencies, services, and routing rules, must be mapped and constructed exclusively on the configuration side of this boundary. This establishes the absolute rule for XMF developers. Runtime controllers must never instantiate their own infrastructure dependencies. Enforcing this strict boundary is the only way to allow selective component substitution and comprehensive mock testing without requiring destructive controller rewrites. When a standard API mutation request comes in, it hits the post-API controller on the runtime side of the boundary. The controller has exactly two jobs: validate the incoming payload and mutate the core entity state. Embedding cache updates, notification triggers, and audit logging within that same controller creates bloated code. To decouple these secondary operations, we use the domain event pattern. A glowing event token fires from the controller across the boundary directly to a central event bus. The exact moment the entity saves, the controller dispatches a specific domain event, like the post-published event. The event bus intercepts this dispatch and instantly splits it, routing the event simultaneously to all registered infrastructure listeners. One of these paths immediately executes a complex cache invalidation routine entirely outside the controller's awareness. Because of this event-driven decoupling, the primary controller process terminates immediately, dramatically reducing user-facing latency. The remaining event paths are routed directly from the event bus into the queue system, stacking into discrete data packets for delayed background processing. To ensure reliability, these asynchronous job payloads are kept small and strictly serializable. This allows operations like dispatching emails or updating analytics to process safely in the background, entirely separated from the web request cycle. By combining centralized composition routes, event buses, and async queues, we provide the infrastructure necessary to run enterprise-grade SaaS patterns inside the legacy XOOPS ecosystem.